The giant Magellan telescope takes shape this week on Planetary Radio. Welcome to Public Radio's travel show that takes you to the final frontier. I'm Matt Kaplan of the Planetary Society. It will dwarf every current optical instrument, including the twin Keck eyes atop Mauna Kea in Hawaii. Patrick McCarthy is in charge of creating the GMT, one of a new class of super or extremely large telescopes. We'll visit with him at his base of operations. Emily Lakdawalla will reveal a new explanation for the bad case of acne on the face of Mars, while Bill Nye, the science and planetary guy, will tell us how a solar sail may one day test a weird prediction made by the theory of relativity. We'll close with a quick look at the night sky from Bruce Betts, recorded immediately after the Planetary Society open house a few days ago. Emily Lakdawalla gets us underway with highlights of the blog at planetary.org. Emily, good to see you at the Planetary Society's open house last week, especially with your 3D camera.
Yeah, I had fun shooting 3D photos of all the people who came out. There were lots of members who came to support the Planetary Society, and a few big names like a certain Apollo 11 dancing astronaut, Buzz Aldrin. That was the first time I had actually met him, so that was exciting for me.
Oh, really? Yeah, he was great. He had a nice little statement in support of the Society. It was fun to have him. And I got to move his car because he'd parked it in some federal judge's spot next door. But let's talk about planetary science. Beginning this week with these, you call them enigmatic little mounds that everybody's been trying to figure out what generates them on Mars.
That's right. There are these little kind of pimply mounds that cover this huge region on Mars called Acidalia planitia. It's a large low-lying plain in the high northern latitudes of Mars. And if you look at the geologic context, there are a lot of these huge outflow channels on Mars, all of which eventually empty into Acidalia. So it's not a stretch to imagine that at some time there was a lot of water here, a lot of fine sediment. But now, of course, everything's dry. And as you zoom in and zoom in and zoom in on the images that we're getting from Mars Reconnaissance Orbiter, you see that these little mounds are everywhere and that they tend to line up along cracks between huge polygonal fractures in the plains. And I just read this interesting paper that describes how, because of the way that they're shaped and the way that they align along the cracks and the geologic context, they think that they are probably past mud volcanoes, places where gas and water and mud and rock spewed up out of the ground and made these tiny little mounds that there's tens of thousands of them across the northern plains of Mars.
Are there parallels to these structures down here on Earth?
There are some on land, including I have a Google Earth image of some that are in Azerbaijan, but I think they're actually more common underwater in the ocean basins.
Well, we'll put up a link to that at planetary.org on the this week's show page. Just one other thing to mention, and that's another bit of your excellent work, taking images from a mission and making them even more interesting, this time with the animation of some moons.
That's right. I love it when Cassini captures movies of moons in motion. And of course, Cassini doesn't capture movies on its own. It just captures single frames, but the moons move in front of it, and all you have to do is stack the frames together and animate them. And this one was particularly cool because it was unusually close to some very small moons when it gathered this animation. So we see Prometheus, Epimetheus, Janus, and Atlas all crossing through the field of view. And we're close enough that you can see how Prometheus is elongated, this two-lobed yam shape, and how Epimetheus has a nose sticking out of it, and there's craters on Janus. It's a really fun little animation.
Very cool work, Emily. Thanks once again for all you do and for joining us on the show.
Thanks, Matt.
Emily Lakdawalla is the Science and Technology Coordinator for the Planetary Society and a contributing editor to Sky and Telescope magazine. Here's Bill.
Hey, Bill Nye, the planetary guy here, soon to be executive director of the Planetary Society. And this week I have been thinking. My mind has been dragged around, if you will, from a lecture I heard a couple weeks ago at the International Solar Sail Symposium that Lou Friedman and I attended and presented our light sail project. I saw a lecture by Roman Kirchiavili. He's a big solar sail proponent. And he talked about an old phenomenon that's been theorized called frame dragging. So you have a really massive object like the sun, and you have a very, very sensitive instrument, like the amazing accelerometers that are going to be on Light Sail 1. And you get an orbit around the sun, and there'll be a relativistic effect such that space-time is distorted, is dragged. The frame of reference is dragged. It seems slower to people farther away, faster to people closer, crazy things like this. And we could use our solar sails to detect this. We could show another aspect of relativity to be true, or stranger still, show another aspect of relativity that you'd expect to be true to not quite be true, which would be even crazier. This is called the Lenz-Thirring effect, named after a couple of physicists who first talked about it back in something like 1918. And this is an exciting thing. And if you're a member of the Planetary Society, it's another thing you're participating in. We are exploring space using the only propulsion technology usable for going between stars. I'm talking about solar sailing. It's the pressure of photons nudging very low mass spacecraft through space. It's exciting. I gotta fly. Bill Nye, the Planetary Guy.
It's just a stately-looking building on a quiet street in Pasadena, California. Yet it has been the birthplace of several of the world's greatest scientific instruments. Another is taking shape there right now. The giant Magellan telescope is just one of the tremendous reflectors now being designed and built. Another, the 30-meter telescope, or TMT, is headquartered a few miles away on the campus of Caltech. Pat McCarthy directs the GMT project for the Carnegie Institution of Washington and an international group of partners. He took me into the parking lot to get a feel for just how big this new scope will be. There on the asphalt are 6 painted circles surrounding a 7th. Each of those circles represents one of the GMT's 7 mirrors, and each is 70% larger than the single mirror in the 200-inch or 5-meter Hale telescope on Palomar Mountain. One of my favorite places on Earth is Palomar. And I have said to many people, including the audience of this show, you really don't get a sense of the scale of that instrument from any photograph I had ever seen during my entire life, the way you do when you show up there.
Yes.
This helps, but the scale of this compared to that instrument, the 200-inch, is just overwhelming.
It is overwhelming. So imagine, take one of these circles. These are 8.5 meters in diameter. Palomar is 5 meters. So you stand about here and to that edge. That's the Palomar mirror. So the scale it's hard to comprehend. But an interesting fact I like to tell people is that Palomar, the moving weight of the telescope is 770 metric tons. The moving weight of the GMT will be 1,100 metric tons. Now, that's less than a factor of 2, but it's more than a factor of 10. It's about a factor of 20 gain in collecting area and only a factor of 2 increase in mass or weight. So that shows you that advances in engineering, computer-controlled drawing, finite element analysis allow you to build structures that are much more mechanically efficient. And the fact that the optics are very fast allows you to build structures that are compact. So we're gaining a huge factor in collecting area, less than a factor of 2 gain in mass and weight. And mass and weight translated to cost, performance, and so on. That's what makes this possible. If you scale the 200-inch up, it would be a behemoth like the pyramids and it would collapse under its own weight. You couldn't possibly do it.
Pat, we've retired to this beautiful library, part of the Carnegie facility here. There is a wonderful photo as you enter that kind of gives me goosebumps.
Yeah, well, there's a lot of history in this library. Einstein spent a couple of summers here at Mount Wilson back in sort of the critical days when cosmology was taking off, general relativity was just being formulated, and there's a great photo of him giving a lecture beneath the portrait of Hale, and Einstein is standing in front of a blackboard, and he's written an equation, R equals 0, question mark. And he's asking, in essence, is the universe curved or is it flat? And that has profound consequences. Will the universe expand forever? Will it collapse upon itself? Or will it actually be right on that fine dividing line in between? If you had asked Einstein at the time, the one thing he was confident is that it was not at that fine dividing line in between. He didn't believe the universe could actually be flat, in part because of the cosmological constant he had invented and then discarded upon Hubble's observations. And now, of course, we've come full circle. The universe is flat. The cosmological constant rules, or dark energy. We're not exactly sure which it is. And, the history carries on, but much of it started here, and it's still going on. And this is just a wonderful bit of history and a nice piece of architecture here as well.
Doesn't make much sense over the years for anyone to contest Albert's concepts, even Albert himself.
It's generally not been a winning strategy. Yeah.
Really, it makes for quite an environment to be designing one of the great new generations of telescopes.